All right, so History of Math Lecture 3, there's a question about the homework problem number 5, which has to do with the geometrical shape called a frustum. So you take a pyramid with a square base, and imagine that all right, so that's the pyramid with the square base. But if you cut off the top piece, so I'll cut off the top piece by erasing, that's a frustum. And the base is a square of side A, the top is a square of side B, and the height of the frustum is H. And that's the frustum. And to compute the volume of the frustum compute the volume in the case when the height is 7, the base is a square of side 9, and the top is a square of side 6. So I'll do it in 2 ways. In part C, we're supposed to prove the formula that the volume is a third of the height times a squared plus ab plus b squared. Right. Is there a question about this? So if I were to use this formula, I would get the volume is h, which is 7, over 3, times a squared, 81, plus ab, which is 54, plus b squared, which is 36. So that's 7 over 3. If you add this up, 54 plus 36 is 90, plus 81 is 171. 3 divides into 171 57 times, I believe. And 7 times 57 is 399. So that's the volume of this frustum. Is there a question? Question? Okay. So how do we get this formula? Well, in general, this is really something which is often proved in calculus. If you take any shape in the plane, doesn't matter what it is. So this is in the plane, and you pick a point and at a certain height above, and you draw this sort of, let's call this region R. So this is sort of like the cone with base R, and height H. So it can be, an ice cream kind of cone where the base is a circle. It can be a pyramid of any size. Let's say the base is a square. But you take any region in the plane and a point above it, and you construct this cone, sort of a generalized cone, if you like, with height H, base R, and height H. And if the area of the base is equal to, let's say, A for area, you see, if instead of constructing the cone, let's say you constructed what we call the cylinder. So you take some region in the plane and you just construct a cylinder over it. So it's just like as if you took this region R that's in the base and you lift it a height h, and you have this cylinder. So associated with any region in the plane, you can construct the cylinder or you can construct the cone. And again, if the area of the base is equal to A, the volume of the cylinder is just the area of the base times the height. Right? I mean, if you think of an ordinary cylinder with a circular base, it's the area of the base times the height. In general, the area of a cylinder is the area of the base. The volume of a cylinder is the area of the base times the height. And the volume of the cone, this is one of the amazing facts in calculus or geometry, is a third the volume of the cylinder. So it's a third the area of the base times the height. So that's a formula for the volume of a cylinder. Right? Now, how do we get the volume of the frustum? So you can imagine, let's say, here's your square base. Suppose we construct the pyramid over that base. So the base is a square of side B, and let's say the height is, so the height of the pyramid is capital H.
Would it be like B squared, like 1/3 B squared H?
Well, that would be, so the volume of the pyramid is 1/3 the area of the base times the height, capital H. So that's the volume of the pyramid, right? But we don't want the volume of the pyramid. We're going to cut off the top of the pyramid and we want the area of the frustum, which is the part that's left. So if we chop off the top of the pyramid, what's left in blue is the frustum. And how much of the pyramid do we chop off? Well, we cut off a piece of the pyramid where the base of this little pyramid is A. So what we're chopping off is a pyramid whose height is A, whose base is A, and whose height is little h. So the little pyramid, the little red pyramid, has volume V equal to 1/3 the area of the base h squared times, I'll call it h prime. H prime is the height of the little pyramid, just as capital H prime, just as capital H was the height of the big pyramid. But we don't know what this is unless we know what H prime is, right? What is the height of this little pyramid? We know the base, but we have to figure out the height. So we can use some geometry for that. Imagine you took a slice through this pyramid, let's say from the top down to the center, right? We have a triangle. Let's see. So imagine from the top of the pyramid, you drop the vertical line to the base. It hits the base in the center of this square. And this height is capital H. And this Well, what is the distance from the center of a square? Let me use another piece of paper. Suppose you have a square of side B. So here's the center, which means the distance from here to here is B over 2. The distance from here to here is also B over 2, right? This is sort of the midpoint of the, and what is the distance from this vertex, the center, to the corner? Well, this is a right triangle, it's isosceles. So, you know, if you have a triangle, a right isosceles triangle, if the side is x, the hypotenuse is x times the square root of 2. So the length of this is B over 2 times the square root of 2, right? Or B over the square root of 2. That's the base, that's the distance from the center of a square of side B to any one of the 4 corners of the square. So let me just stop for a second. So this is the kind of geometry you're certainly supposed to know, right? It's just the Pythagorean theorem. You have a square of side B, you take the center, distance to each side is B over 2, distance to the corner is B over 2 times the square root of 2. So if you go back and look at our pyramid, in this pyramid, if you take the vertex, the top of the pyramid, drop the vertical line to the base, it hits the base in the center, draw the line from the center to any vertex of the square base, that's a right triangle. And this height is capital H. This is B over 2 times the square root of 2. That's what that right triangle looks like. Now, again, just as we had a moment ago, if you had a square of side A and you take the center, the distance from the center to the corner is going to be square root of 2A over 2. So if I were to go up a certain height where, and draw this perpendicular, where this is square root of 2A over 2, that's exactly what I get if I go to my pyramid, I drop this vertical line to the base, I have this right triangle, and then I also look at the right triangle I get by cutting off a piece of it, this the bigger triangle, where it's cutting off, I'm making this horizontal slice where the side of the square is A. So in particular, this base of this little triangle is square root of 2A over 2. So this height of the whole triangle is H. And what is the height, which I called capital H prime, of the little triangle? Well, if I call this A, B, C, maybe D and E, the triangle ABC is similar, that means proportional, to the triangle CDE. So the ratio of the sides are proportional. So the ratio of the height from C to D, or the length of this line from C to D, the line from C to A, which is exactly H prime over H, is going to be the same as the ratio of this line to this line, which is the square root of 2A over 2 divided by the square root of 2B over 2, which is A over B. So capital H prime is A over B times H. So if I look at this slice through the pyramid, if the base is B and the height is A, the height of the small red pyramid is like A over B times the height of H. So H prime is A over B times H, but I'm interested in the height, well, little h, or I want to know what is the height of the frustum. Little h is just the big height, h minus a capital H minus capital H prime, which is h minus a over b h, which is a over b, which is, if I factor out the h, is h times 1 minus a over b. Okay. So looking at this picture, the volume of the big pyramid is 1/3 h b squared. The volume of the small, that's the red pyramid, is 1/3 h prime b squared. The difference, if I take the big pyramid, I chop off the top, I'm left with the frustum. The volume of the frustum, which is what I want to figure out, is the whole volume, 1/3 hb squared, minus the little volume, 1/3 h prime b squared, which is capital H minus h prime over 3 times b squared. This is my little height. This is h. That's equal to h. All right. I should be almost done. So let me just go back and review how I got to this point. Okay. So this is like a geometry problem. Maybe an honors geometry problem if you're teaching geometry. You want to find a formula for the volume of a frustum.
Professor, is this a problem from the homework?
Problem number 5.
Okay.
Right. You want to find the volume, a formula for the volume of the frustum. You want to prove that the volume is 1/3 the height times a squared plus ab plus b squared, where a is the volume of the base and b, a is the length of this, the base is a square of side A, the top is a square of side B. So we want to prove this formula. So I'm going to try to prove it by using the formula for the volume of a cylinder, so the volume of a cone. A cone always has volume 1/3 the height times the area of the base. So my frustum I can obtain by taking the cone over, I like drawing pictures, so let me just do this again. I have a square of side A, and I construct the cone over that square. And at a height, little h, above the base, I slice off the top. I slice off the top of the cone. And what's left underneath is my frustrum. So this area in blue equals frustrum. That's what I want to calculate. I have a red pyramid on top. That's the top of this. Okay. So let's say that the height of this whole cone is capital H, the big cone. And if I want to, so I want to find out what is capital A. So the volume of the frustrum equals the volume of the big cone minus the volume of the little red cone. The volume of the big cone is a third the height times the base. The volume of the little red cone is a third the height of the little red cone. That's actually going to be the height of the big cone minus the height of the piece that's left after you chop off the red piece. The height of the red cone is 1/3 capital H minus little h, A squared. That's a simpler formula for, that's the area of the frustrum. It's the area of the big cone minus the area of the little cone. So let's see, what is that? That's, sorry, B, this is a B. Area of the base of the little cone. So this is 1/3 H, just rearranging this, A squared minus B squared, plus 1/3 H, B squared. 1/3 little h. So I'm just expanding this. I get a third H, capital H A squared, minus a third capital H B squared. That gives me this. Minus times minus is plus 1/3 little h times B squared. Right? So what I need to do is compute capital H. I have to know what that is. So if I look at the triangle that I get slicing through the pyramid, I have, this is capital H, this is little h, so this is capital H minus little h. This is, we calculated that, it's A over the square root of 2, and this is B over the square root of 2. And by similar triangles, this red triangle is similar to the whole big triangle. The ratio of this height to the big height, h minus little h over capital H, is like the ratio of the bases, A over root 2 over B over root 2, which is A over B. And I can solve this equation for capital H. This says h minus little h is A over B times H. Or rearranging this, little h is H minus A over B times capital H, which is H times 1 minus A over B, which is H times B minus A over A. Or just bringing this to the other side, capital H is A over B minus A times little h. So if I take this formula for capital H and plug it in there, what do I get? I get the volume that I'm looking for is 1/3 capital H, that's HA over B minus A, times A squared minus B squared, plus 1/3 HB squared. But they teach you in algebra how to factor A squared minus B squared. A squared, oops, sorry. This is the short, this is B over root 2 over A over root 2. So this is B over A. So that's A minus B over A. So the reciprocal, this is A minus B. And A squared minus B squared is A minus B times A plus B. And the A minus B in the denominator cancels the A minus B in the numerator. So what I get is H over 3 A times A plus B plus H over 3 B squared. If I factor out the H over 3 and expand, I get A squared plus AB plus B squared. That's actually the good proof of this result. So that's the proof, right? I mean, that's I mean, one of the main purposes of this class is to teach you parts of the history of mathematics that are relevant if you become a middle school or high school math teacher, for example, where you're teaching geometry, and every bit of this proof is part of basic geometry. But the hard thing to learn in mathematics often is how to put together a large number of basic steps, small steps, to get the main result that you're hoping for. But this is the proof, right? It might take a lot of
Professor,
time
is
to work
that-
out, but
Professor,
yeah, question.
is that H over 3?
Little h over 3, right? I
Little
mean,
H over 3?
that's what's stated in the problem. So if you look at problem 5 in the homework,
Mhm.
problem 5, part C, is to
Mhm.
prove exactly this formula. Little h over 3 times A squared plus AB plus B squared. Right?
Thank you, Professor.
Again, there are a lot of steps in the proof, and but that's the proof. Okay. Any other questions about the homework?
Yes, Professor, can we do problem 3?
Sure. Homework number 3. So we're looking at what are called Pythagorean triples. If you have a right triangle with sides x, y, and hypotenuse z, x squared plus y squared plus equals z squared. That's this amazing result called the Pythagorean theorem. And part A is to prove that at least one of the numbers x, y, and z is even. So what you have to remember is when you're adding numbers, even plus even is even, odd plus odd is even plus odd is odd, right? So you know this, but you have to see the relevance of it. And since the words even and odd come up in this problem, this is one obvious thing to think about. You have to show at least one of these three numbers is even. If x and y are odd, I should also say even times even is even. An even number times an odd number is even. And the product of two odd numbers is odd. So if x and y are odd, then x squared, which is x times x, is a product of two odd numbers. And y squared, which is y times y, is a product of two odd numbers. So these are odd, which means x squared plus y squared, a sum of two numbers, z squared is even. And if z squared is even, z is even. So if you look at x, y, and z, you want to show at least one of them is even. If x is even, you're done. If y is even, you're done. If x is odd and y is odd, x squared plus y squared, which is z squared, is even. So z has to be even. So at least one of the three numbers has to be even. So that's the reasoning, right? That's the logic. Question about this?
I was gonna ask, cause since this is, we're talking about a Pythagorean triple, these are like lengths of the sides of a triangle, correct? So,
These are numbers.
oh, these are just okay.
Well,
Okay.
again, if you look at the problem carefully, it says a Pythagorean triple is a triple of positive integers x, y, and z. So in this problem, x, y, and z are not only numbers, they're integers, they're whole numbers.
Okay, so it's not specifying anything about, oh, that this is a length or anything, so.
No,
Okay.
it just says they're positive integers.
Okay.
Okay. Part B is to prove that if two of the integers are even, the third is even. So if x and y are both even, then x squared, y squared are even, because this product of two even numbers is even. The sum of two even numbers is even. So z squared is even. So z is even. So if x and y are even, so is z. If x and z are even, then x squared and z squared are even. If you look at the equation, z squared minus x squared is y squared. The difference of two even numbers is even. So y squared is even. So y is even. Okay. So that's, so if two are even, all three are even. And how do you construct a Pythagorean triple in which all three integers are even, well, I don't know. I mean, you take your most famous Pythagorean triple, 3 squared plus 4 squared is 5 squared. Of course, these aren't all even. 3 and 5 are odd. Suppose I multiply by 4. I get 4 times 3 squared plus 4 times 4 squared is 4 times 5 squared. Let's see, 4 times 5 squared, 4 is 2 squared times 5 squared, which is 2 times 5 squared, which is 10 squared. And similarly, 4 times 3 squared, actually you can just check the arithmetic, that's 6 squared. And 4 times 4 squared is 8 squared. So 6 squared plus 8 squared equals 10 squared. And that's a Pythagorean triple with the numbers 6, 8, and 10. That's my Pythagorean triple. And they're all even. So one simple way to get a Pythagorean triple with all even numbers is to take any Pythagorean triple and multiply all the numbers by 4 or by any number that's the square of an even number. That will do it. Okay.
Professor, where did you get the 6 square plus 8 square?
Well, I have 4 times 3 squared, right? Do you see
Yeah.
that?
Yeah.
What is that? 4 times 9. What's 4 times 9? What's 4 times 9?
36.
Right. What's 6 squared?
36.
Okay. So 4 times 3 squared is 6 squared. And in the same way, 4 times 4 squared is 8 squared. That's where I got it. I took 3 squared plus 4 squared equals 5 squared, and I multiplied the equation by 4.
Oh, okay.
Okay.
Okay, thank you.
Any other homework problems that I should look at? Let me do number 7. An algebraic number is a number x that is the root of a polynomial equation, of a polynomial with integer coefficients. And a transcendental number is a number which is not algebraic. So you take any real number, it's either algebraic or transcendental. Transcendental just means not algebraic. So suppose I take x equal the square root of 7. then x squared is equal to 7. So x squared minus 7 is 0. So this is a polynomial. I call this f of x. F of x is the polynomial x squared minus 7. The coefficients are 1 and 7 or minus 7. They're integers. And f of the square root of 7 is 0. So the square root of 7 is algebraic. What about x equal to cube root of 2 plus 1?
Wouldn't that be a polynomial of parentheses x minus 1 cubed plus 2?
So let's see. If I take x minus 1, that's going to be the cube root of 2. So if I cube both sides, x minus 1 cubed is the cube root of 2 cubed. Of course, if you cube the cube root of 2, you get 2. And if you cubed x minus 1, you get x cubed minus 3x squared plus 3x minus 1. So we have that, if I bring this to the other side, x cubed minus 3x squared plus 3x minus 3 equals 0. So this is a polynomial for which cube root of 2 plus 1 is a root. Right? So f of cube root of 2 plus 1 is 0. So this is a root of this polynomial of degree 3. So it's exactly what you said. Let's see, let's look at the number a little more complicated. X is the square root of 2 minus the cube root of 2. Now, you start with a lot of information because I'm telling you in the problem that this is an algebraic number, and we have to prove it's algebraic by constructing a polynomial for which this is a root. So one way to do this might be the following. Let's see. The cube root of 2 is going to be the square root of 2 minus x. I just rearranged this equation. And if I cube both sides, what do I get? On the left, cube root of 2 cubed is 2. And on the right, well, that's a little bit trickier. Just expand this. Cube root of 2 cubed is 2 root 2 minus 3 root 2x. No, sorry. Minus 3 root 2 squared x plus 3 root 2x squared minus x cubed. See, what is this polynomial? They just write this. All right, so this says 2 is 2 root 2. If I square root of 2, I get 6. 3 times 2 is 6. Sorry, if I square root 2, I get 2. 3 times 2 is 6. Plus 3 root 2x squared minus x cubed. So x satisfies this equation, but the coefficients involve a square root of 2. They're not integers. So I have to do something sneaky to deal with that. Let's see. Another way of writing this is 2 equals something times the square root of 2. 2 plus 3x squared times the square root of 2 minus 6x plus x cubed. So, and that's, I hope I did the little bit of algebra right. X is root 2 minus cube root 2. So cube root of 2 is root 2 minus x. If I cube both sides, I get 2 equals root 2 cubed, which is 2 root 2, minus 3 times 2 times x, plus 3 root 2 x squared minus x cubed. So that's 2 root 2 plus 3x squared root 2. If I factor out root 2, that's root 2 times 2 plus 3x squared minus these two terms, that's minus 6x plus x cubed. So again, if I rearrange that, I get 2 plus 3x squared times the square root of 2 equals x cubed plus 6x plus 2. So if this is correct, I hope it is, I have this equation. Now I square both sides. So square both sides. If I square the left-hand side, I get 2 plus 3x squared squared times the square root of 2 squared, which is 2, equals x cubed plus 6x plus 2 all squared. And if I look at this, I have a polynomial, and there are no coefficients that are not integers. Another way of writing this is x cubed plus 6x plus 2 squared minus 2, 3x squared plus 2 squared equals 0. This is a polynomial. X cubed squared is x to the 6th. This is a polynomial. The degree is 6, and the coefficients, when I expand it, are integers. So my number x, this guy, is a root of this degree 6 polynomial with integer coefficients. That's the story. Right. By the way, what's nice about this problem is it makes an easy exam problem, because it's always hard to find problems that are not too long and just involve some algebra. So what is almost certain to be a midterm exam problem will be, I give you a number, I say it's algebraic, and I ask you to find a polynomial for which that, with integer coefficients, for which that number is a root. Okay. All right. Well, we have a simple syllabus in this class. Every week, we do a chapter, and this is the second week. So this week, we do chapter 2. And chapter 2 is more Greek mathematics, but more geometry in particular. And it's centered on the Pythagorean theorem. That's the great theorem in this chapter that we will end up shortly proving. But this chapter and the next chapter are really devoted to the most important book ever written in the history of mathematics, and what many people think is the book that has had the most use, the most published editions of any book in the history of the world except the Bible. So if you were to look at the New York Times bestseller list for the history of the world, number 1 would probably be the Bible, and number 2 would probably be Euclid's Elements. So the elements, it's actually it's divided up into sections that are called books, and it involves more than geometry. It involves geometry, arithmetic, or what we call number theory, and not just two-dimensional geometry, but 2 dimensions and 3 dimensions. So we look at things like volumes in 3 dimensions, the way we look at things like area in 2 dimensions. We saw in chapter 1, Hippocrates, his quadrature of the lune, which was from around 440 BC. Euclid was from around 300 BC. It's a 140-year difference. If you go back 140 years from today, you're back around 1880. What people knew about mathematics in 1880 compared to what we know today was infinitesimally small. In 1880, people knew very little about the physical world. They didn't know that matter consisted of molecules, molecules consisted of atoms, atoms consisted of protons, neutrons, and electrons. Protons consisted of smaller bits called quarks, that there were large numbers of other particles in matter other than protons, neutrons, electrons, and their constituents. People knew very little 140 years ago. But the increase in knowledge from 440 BC to 300 BC, the same period of time, was really very little. I mean, the rate of progress in the world in the 19th, 20th, and now 21st centuries is unbelievably fast compared to the past history of things. But Euclid, in around 300 BC, wrote his series of books that summarize a lot of the mathematical knowledge of the time. So what Euclid did was, it's very hard to know who did what when that long ago. But it seems that Euclid really organized, he wrote a textbook, a great textbook in mathematics, organizing the mathematics of his time. And he introduced a method, or at least he made explicit, what is sometimes called the axiomatic method, which means this notion of proof. You don't know something is true in mathematics unless you can prove it. And you can't just start proving things from nothing. You need some preliminary definitions, rules of inference, postulates that you start from. So these are given as true, but whether they're true or false, it really is irrelevant. It's not even clear what that means. These are the statements you start with, and then using your principles of proof, your principles of deduction, you see what you can deduce from what you start with. So the starting points for Euclid, there are certain definitions. He defines a point. He defines a line. He defines a straight line. He defines what it means for two lines to be perpendicular. He defines a circle. He defines what it means for lines to be parallel. Now, you might say some of his definitions are so vague they're almost meaningless. So, for example, he says a point is that which has no part. So in geometry, you talk about points. What is a point? Well, he gives a definition, but maybe the definition doesn't really mean anything. A point is that which has no part. So somehow in your mind, in your brain, in your imagination, you have to develop some feeling, some intuition of what a point might be. But a point is just something. There's something in geometry called points. And Euclid says it's that which has no part. If that makes sense, that's great. If it doesn't make sense, it doesn't matter. A point, you have some objects called points. What is a line? A line is breadth. This length. Breadth is the same as width. This means a line is something which has no width. I mean, you think of this as a point, you think of this as a line. Of course, this has width because the lead of my pencil produces a thickness when you use it, but the line is breadth plus length. Whatever that means is certainly when you talk about a line, you cannot talk about the width of a line. The line has no width or no breadth, it only has length. A straight line is a line which lies evenly with the points on itself. Again, you should, it's good during the lectures if you have your book with you. This is on pages 32 and 33, where some of the definitions from the beginning of Euclid's Elements are written down. Very important is definition 10 for perpendicular. And perpendicular means the following. You have a line and you have a straight line. It says when a straight line standing on another straight line. So here is a straight line standing on this straight line. Here is a straight line standing on this straight. These both examples of straight lines standing on a line. The angles between the baseline and the line which is so-called standing on it, these are called adjacent angles. Here, the adjacent angles are different. Here, the two adjacent angles are equal. So, if the adjacent angles are equal, which occurs in this case, then we call the angles perpendicular. So in the definition of perpendicular in Euclid, there's no measurement of the angles. It's not that angles are perpendicular if they have 90 degrees or pi over 2 radians. The definition of perpendicular is the following geometrical one. If you have one line standing on another line, if the adjacent angles are equal, then those angles are called perpendicular. That is the only definition of perpendicular in Euclid. What is a circle? So a circle, this is the definition in Euclid, is a plane figure where there's some point, and if you take any line segment from that fixed point to the figure, all these lines have the same length. So we would say this is a circle with this is the center and this is the radius. But the geometrical definition, the only definition in Euclid for a circle is you have some curve in the plane and at some point, and the line segments from that point to any point on the curve have the same length. These all have the same length. And in the history of mathematics, one of the most important definitions is the definition of a pair of lines that are parallel. That is the definition of parallel lines. So definition 23. Parallel straight lines. We don't talk about parallel curves. Parallel straight lines are straight lines in the same plane, which when you extend them to infinity in both directions, or as the translation from Euclid reads, lines produced indefinitely in both directions do not meet in either direction. So these would be parallel lines. You can go out this way forever, you can go out this way forever, and the lines never intersect. So these lines are parallel. Lines like this, which intersect somewhere, are not parallel. Okay, any questions about this? Now, in addition to the definitions, there are some postulates, some statements. So postulate 1 says if you have 2 points P and Q in the plane, it's possible to draw a straight line from P to Q. Okay. Since it's all written down legibly in the book, I don't need to write everything down. Postulate 1 says it is possible to draw a straight line, or if you like, a straight line segment from any point to any other point. Postulate 2 says if you have a line or a line segment, it can be extended continuously in both directions. So if I start with this line segment, I can extend it forever in both directions. Postulate 2. You can think of this postulate 1 as saying something about the existence of a straight edge. That is, given 2 points P and Q, you can take your straight edge and draw a line between P and Q. That's all you can do. Postulate 3 says if you have any point, call it 0, and any distance or line segment, you can construct a circle with center at 0 and your given length as the radius. That is, given a point 0 and given some line segment, you can construct the circle, the figure in the plane, where the line segment from the center to any point on this so-called circumference is the same, they all have the same length, the same radius. Right? It is possible to describe a circle with any center and distance. Now, what you cannot do, so this postulate 1 can be something like the existence or the permissibility of using a straight edge, not a ruler. You can't mark distances on your straight edge. Postulate 3 about the existence of a circle says something about the use of a compass. Compass means if you have a compass, here's a compass. I can take any point as a center, and if I had a line segment, I can draw a circle with my given center. And every radius, every line from the center to the circle, they all have the same length as the line I started with. What you cannot do is the following. Suppose I have a line segment AB, and suppose I have some line, and I pick a point C on my line, and I want to find a point D on the line. Such that the distance from C to D is the same as the distance from A to B. Now, you might say, well, here's a way to do it. Take your compass, put one end at A and the other end at B, then lift your compass, move to the line, put one end at C, draw the circle, and where the circle crosses the line, that's the point D. So that's how you can construct a segment on the line of the same length as a given line segment. But in Euclid's geometry, you're not allowed to do that. Because once you have your compass and you use it, as soon as you lift it up, it collapses. It has no memory. So the kind of compass we use is sometimes called a collapsible compass. It has no memory. So you can't use the compass to construct a line segment on somewhere which has the same length as a given line segment. It's a collapsible compass. Your compass has no memory. So in Euclid, there's actually a construction given a line segment from A to B and another line C, how to find a point D where the distance from C to D is the same as the distance from A to B. That can be done in Euclidean geometry without a collapsible compass. You don't need a collapsible compass to do that. And indeed, one of the things you strive for when doing a lot of mathematics is to use a minimal number of postulates when you start. So you don't need a postulate that says given a line segment, you can construct another line segment of the same length. You can actually do a geometrical construction to carry that out. Okay. There are two more postulates, both of which are very important. Postulate 4 says all right angles are equal. That is equal to one another. You have a right angle and another right angle. If you want to think of it like this, you could lift this up, put it down here, and it covers it exactly. All right angles are equal. There's no other angle that is defined in Euclid. There's no 30, 60, 90-degree angles that are defined. There's theorems about such things, but there's no definition of them. And there's one last postulate, postulate 5, which is the one that puzzled people a lot. I'll give it a star because it's so important. It says something about parallel lines, and what it says is the following. Write that down on a separate piece of paper because it's so fundamental. Eight. Postulate 5. So what it does not say is the following. Postulate 5, I'll just write say, does not say, given a line L and a point P not on L, there exists one and only one line through P and parallel to L. So some people think this is the parallel postulate in Euclid, but it's not. This statement says if you have a line L and a point P not on L, there always exists a line through P parallel to L and a unique such line. Right? So this is equivalent, though that's hard to prove, to what Euclid says, but this is not what Euclid says. What Euclid says is the following. If a straight line falling on two straight lines, what does it mean to say two straight lines and then another line is falling on them? It's like here you have two lines, and here we have a line L falling on them. So this red line is falling on, or if you like, intersecting these two lines. So if a straight line falling on two straight lines makes the interior angles so when you have a line falling on two straight lines, there are four interior angles. This, 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 and this. They're the angles between lines L1 and L2 created by this line L falling on L1 and L2. So if a straight line falling on two straight lines makes the interior angles less than two right angles, so somehow if you add, so here we have this interior angle and this interior angle, and these are angles, they're not the same necessarily, but these are the, makes two, sorry, so if a straight line falling on two straight lines makes the interior angles, I should say, on the same side of the line falling, that is, these are two interior angles on the same side as the red line. These two angles are also interior angles on the same side of the line. But if two interior angles on the same side of a line are less than two right angles, then the two straight lines produced indefinitely meet on that side, which are the angles less than two right angles. In other words, these two angles add up to less than two right angles. You take these lines and extend them indefinitely, they're going to cross. So then you say, then the two straight lines meet, which is another way of saying they're not parallel. So this is Euclid's fifth postulate. You have two lines, L1 and L2. You have a third line falling on them, that is, crossing them both. When the line crosses them both, that creates four interior angles. This, 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 and this. These two are on the same side of the red line. These two are also on the same side of the red line, just the other side. these two angles add up to less than two right angles. By Euclid's fifth postulate, if you extend these lines indefinitely, if you stretch them out to infinity, at some point they're going to cross. That's the fifth postulate. And for 2,000 years, people wondered whether this postulate was really necessary or whether it was actually a theorem that could be proved from the other postulates that Euclid gave. And it took 2,000 years or more to answer that question. Now, what does it mean to prove something in mathematics in general and Euclid in particular? You have certain rules of inference, things that you can deduce, that you can say, well, this implies that. What is such a thing? So we might call them rules of inference, but in Euclid, these are called common notions. So common notion number one says things equal to the same thing are equal to each other. So if this line and this line have the same length, and this line and this line have the same length, so if AB is equal to CD and CD is equal to EF, then AB is equal to EF. Things equal to the same things are equal to each other. The common notion number two says equals added to equals are equal. In algebra, we might say that if A equals B and C equals D, then if you add A plus C equals B plus D. This is adding equals to equals. So equals added to equals are equal. And the same thing is true if you subtract. So if A equals B and C equals D, then A minus C equals B minus D. The fourth is a little bit mysterious. Things which coincide are equal. So if this line could be lifted and put on this line and they coincide exactly, we would say these are the same two, or congruent is the word we use now, line segments. And the fifth is the whole is greater than the sum of the parts. Or sorry, the whole is greater than, forget sum, first is false. The whole is greater than the part. So if you have a long line AB, and if AC is part of it, AB is greater than AC, because AC is part of AB. Now, from his definitions, postulates, and common notions, Euclid begins to prove things. And in book 1, proposition 1 says the following. So we can define an equilateral triangle is a triangle with all three sides equal. And proposition says, given a line segment AB, there exists an equilateral triangle, equilateral triangle with base AB. So let me show Euclid's proof. Oops. So we start with the line segment. Fit on my page, so let me draw my line segment in the center. There's a line segment. I want to construct an equilateral triangle with this as the base. So this is what Euclid says. With your compass, using A as the center, and AB is the radius, draw the circle. Draw a second circle, this time using B as the center, and AB still as the radius. These two circles intersect. Pick one of the points where they intersect, call that C. And draw the line segments AC and BC. So we started with AB. AB and AC are radii of the same circle, right? We drew a circle with center at A, radius AB, C is on that circle. So the length of AB equals the length of AC. But we also drew a circle with B as the center and the same radius AB. And AB and BC are also radii. So AB and BC are equal. Things equal to the same thing are equal to each other. AB is equal to AC, AB is equal to BC. So AC equals BC. So these three sides have the same length. So we've just constructed an equilateral triangle with AB as the base. So this is the first result in Euclid. So again, this is, you have a line segment AB, draw the circle with AB as the center and AB as the radius. Draw a second circle with B as the center and AB as the radius. Choose a point C where the circles intersect. ABC is then an equilateral triangle. And if you want to think about something, I mean, it's a beautiful construction, but let me ask the following problem to think about. Why does point C exist? In other words, why do the circles intersect? Okay. So this is really a very interesting question, and if you read the book, there is actually a discussion of this question, which is very important. And I'll talk about this a little bit on Wednesday. Since the great theorem is the Pythagorean theorem, let me say something about the Pythagorean theorem. Pythagorean theorem says something like this. If you have a right triangle, that's my right angle, and say this is A, B, and C. If we called this X, Y, and Z, in algebraic terms, we would say the Pythagorean theorem says x squared plus y squared equals z squared. That's an algebraic statement, and that's not what Euclid is talking about. Euclid is talking about geometry. Here, we have the side x, the side AB of this triangle. Construct a square with AB as one of the sides. For the other leg of the triangle from AC, construct the square with AC as a side. And on the hypotenuse, construct an even bigger square with BC as the sides. So if we label this picture as is done in the text, so let's see. BC DE, that's one square. So we have the square BCDE. Let's label this we have the square ABFG. Let's label this H and K. We have the square AGHK. So on our right triangle, we construct the square on each of the three sides. So the square on the hypotenuse is certainly bigger than the square on either of the two sides.
Professor, wouldn't it be the square of ACHK? I think you
Thank
wrote-
you.
Yeah.
ACHK, yes. So the Pythagorean theorem geometrically says the following: the area of the square on the hypotenuse equals the area of the square on one side plus the area of the square on the other. So Euclid's Pythagorean theorem says you start with the right triangle, construct the two squares on the legs, and the third square on the hypotenuse, and the area of this equals the area of this. And the way this will be proven, I'll do this on Wednesday, is you draw the perpendicular from A, from A through the hypotenuse here. And what we'll prove is the area of this small triangle, small square, equals the area of this small rectangle. The area of this square equals the area of this rectangle. So the sum of the areas of the two squares equals the area of the hypotenuse. That's the Pythagorean theorem. And there's a very beautiful proof in Euclid, which we will do. There are many, 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 many different proofs of the Pythagorean theorem. Just for fun, let me show you an algebraic proof using formulas that we have for the area of a square, a rectangle, and a triangle. So let's say here's our right triangle, X, Y, and Z. So construct a square whose side has length X plus Y. So I can, on each side, divide it into two pieces, one of length X and one of length Y. One of length X and one of length Y. One of length X and one of length Y. One of length X and one of length Y, right? So the area of the big square is X plus Y squared. It's the area of this big square. But after I've marked off lengths of size X and Y on each side, let me draw these lines. And what I see is I have in my square 3 triangles. Each triangle is a right triangle with size X and Y. So this is Z.
Professor?
Yes,
Sorry. Oh, yeah, I was about to ask, could you move the paper up a little? Thank you.
so this is Z. And these are right angles. So the square in the center of side Z has area Z squared. And each of these triangles, it's a right triangle, base X, height Y. Each of these triangles has area XY over 2. Half the base times the height. So the total area, X plus Y squared, which is X squared plus 2XY plus Y squared. This big area is divided up into 4 triangles. I have 4 triangles, each of area XY over 2, plus the area of the square in the center, plus Z squared. 4 over 2, this is 2XY plus Z squared. The X squared plus 2XY plus Y squared equals 2XY plus Z squared. Cancel the 2XYs, you get X squared plus Y squared equals Z squared. So that's one very simple proof algebraically of the Pythagorean theorem. But this is in no way a Euclidean proof. Euclid would not have wanted, appreciated, or allowed this. But it's nice to know there are other ways, not geometric, to prove the algebraic form of the Pythagorean theorem. And this is one of the simplest. Okay. All right. That's everything for today. Again, I remind you, Tuesday and Thursday at 7, I'm on Zoom to answer questions. Also, there's no class next Monday. Next Monday, CUNY is closed. It is somebody's birthday.
That's impressive.
Washington or Lincoln. Lincoln's birthday next Monday. And the Monday after that there's also no class. It's President's Day. So we meet this Wednesday. And then the next class is the following Wednesday.
Thank you, Professor. Have a good day.
Thank you.
Yeah.
Thank you, Professor.
Professor? Professor,
Yes, go ahead.
I have a question. It's in relation to the
Oh, right. So whatever accommodations that you need, you have. There's no question that whatever the Disability Services Office recommended is fine.
Okay, all right, thank you.
There's never a problem with that.
Okay, all right, thank you.
Okay.
All
All
right.
right, bye all.
I have a quick question.
Go ahead.
The second the second proof that you did is considered algebraically,
Yes.
even though you're using shapes which are triangles and squares, Well, yeah, why is it not considered geometrically? Is it because it's not
So I'm
using?
proving it algebraically. I'm taking x plus y and squaring it and crossing off. I'm just doing algebraic manipulations. Also, I'm assigning a number to the area. Like I'm saying the area of the square of size z is z squared. In Euclid, the area of a square is a geometrical shape. There's no number assigned to its area. All right.
All right, so even though it's Z, it's not a definitive number. It's just a
Right,
letter.
but so and you don't assign a number. You don't talk about a number which is the length of a line segment. There's no number associated with it. The line segment is just this geometrical line. There's no number there. You can say one line is twice as long as another, which means if you had a line and a smaller piece, you could lay one on and then the other on, and it would cover these two would cover the first line segment completely. So you can say one line is twice as long as the other, but you can't say one line is 3 inches and the other line is 6 inches. That's not Euclidean geometry,
Oh, okay.
right?
All right.
This is a completely fine proof. It's a lovely proof, but it's not a proof in Euclid. And the proof we give, what is really the great theorem, is the beautiful geometry that's used in Euclid's proof. And we'll see that on Wednesday.
Okay, and then also, did he, with the example with the two circles with the equilateral, did he actually use that term equilateral triangle or?
Yes.
Okay.
Yeah.
All right.
An equilateral triangle is a triangle in which all 3 sides are equal.
Same.
An isosceles triangle is a triangle in which 2 sides are equal. But equal means you could put one line on top of the other and it would cover it completely. It doesn't mean that each is 5 centimeters long.
So he he actually coined all those terminologies that we use today.
Yes. Yes. And there are
Oh.
lots of theorems in Euclid about equilateral and isosceles triangles. And if you read chapter 2, you'll see a number of theorems about them
All right.
from Euclid.
And last question. Is there any theorems or proofs today, I mean that previously that were considered not proven today with the advancements of technology?
So if you look carefully at Euclid, you will find that some of the theorems do not follow from the definitions and postulates. That is, there should have been more axioms or postulates at the beginning of Newton. Everything in Euclid, everything in Euclid is correct. But there are gaps in some of the proofs, including the proof that I gave for an equilateral triangle, because Euclid, because some additional postulates were needed. And at the end of the 19th century, a German mathematician named David Hilbert, continuing a line of work that extended for 100 years, found some additional postulates you need to add to Euclid. A small number of them, but it's some that you needed to add. And with those, every proof is correct. So, but there's nothing in Euclid that's wrong. There are some things where the proofs do not follow the way Euclid says, but in some sense they've been fixed up today because we now have a complete set of postulates or axioms for Euclidean geometry. But anything Euclid said was true is true.
And also anything that could be proven geometrically can also be proven algebraically as well.
I don't know. Only because there's a huge amount that can be proven geometrically. I don't know if you can always translate the proof into algebra. Just as in the other direction, there are a huge number of things you can prove algebraically, and I don't know whether you can give geometric proofs of them.
Oh, okay. Thank you very much.
Okay. Bye all.